Hello everyone, I'm Mitsuru Arita, a master first degree student in Kyushu University, Japan. The title of my presentation is ZEL, Net Zero Energy Lifelogging System using Heterogeneous Energy Harvesters. This is the outline of my presentation. First, I'm talking about background and motivation. Nowadays, many office workers have a problem with their lifestyle. It can be caused by such as lack of exercise and sitting all day. Lifelog is a good way to review our lifestyle. For supporting the review, we can use wearable devices such as Apple Watch and Fitbit, which record the lifelog. Then, let's look at the architecture of a typical lifelogging system. Mainly, it consists of three components. From left to right, sensors, microcontroller, and battery. The battery, like a lithium polymer, supplies power to sensors and microcontroller. And the microcontroller acquires sensor signal, then records it or transmits it by wireless communication. Of course, a typical lifelogging system requires battery to be charged periodically. For example, the Apple Watch needs to be charged every day. Fitbit will run longer than Apple Watch, but it also needs to be charged every week. Because the capacity of the battery is limited in small wearable devices. Needless to say, it is bothered to charge a battery periodically. But how can we achieve zero energy lifelogging? The straightforward solution is powered from energy harvesters. Energy harvesting is a technology that converts ambient energy into electrical energy. Solar cells and piezo elements are the common energy harvester. By replacing batteries with energy harvesters, the battery can be eliminated. But to ensure continuous operation, the size of the harvester must be large. For small wearable devices, this solution is not realistic. So when powered from energy harvester, intermittent operation using capacitor is often used. Intermittent operation means to repeatedly charge and discharge the energy as shown in the figure below right. Intermittent operation can reduce the size of the harvester. But to drive the high-powered sensors, it takes a lot of time to store energy. So high-frequency recording is not possible, and it will lead to low-quality lifelog. So we considered how to realize a zero energy and high-quality lifelogging. In 2019, our research group showed that energy harvesters can be used as a sensor for lifelogging. A half energy harvesters as a sensor. This study's main idea is harvested signal has context information for Lifelog. Here is a simple example. If the generated energy by the solar cell is low, it has information that the place is dark. So by inputting the signal patterns into the machine learning model, we can estimate where it is here. By using harvesters as sensors and power sources, we achieved the simple architecture shown in the figure. We were able to eliminate the battery and even the sensors. Here are some related works. Mar has proposed walking detection system using piezo element. They embedded piezo element into the shoes and simultaneous energy harvesting and walking detection. Sanju proposed SOLAR, solar activity recognition. They used solar cells as activity recognition sensors and power sources. But neither research has resolved the key challenge of implementing an energy harvesting function on a small wearable device that could then be used for achieving long-term lifelogging. So our study's goal is to propose and implement net zero energy lifelogging system. Net zero energy means that the energy consumed by the overall system is almost covered by energy harvesting. The reason why net is a small battery for timekeeping is essential for lifelogging. By designing circuits that minimize battery usage, we aim to eliminate battery maintenance. Next, I'm going to talk about proposed system. Our ZEL consists of two blocks, date collection block and lifelog generation block. First, I'd like to talk about date collection block. Date collection block is implemented in a name-type shaped device. It records the harvested signal pattern with net zero energy. ZEL has three harvesters. One dye-sensitized solar cell, one amorphous solar cell for place recognition, and piezo element for activity recognition. Amorphous solar cells are highly affected by the ambient due to their unstable characteristics. On the other hand, dye-sensitized solar cells have stable characteristics and can be expected to generate a certain amount of power even in dark place. By combining these solar cells, we aim to develop a system with high accuracy and a wide operation range, and minimize the battery usage by switching operation mode using two comparators. This mechanism achieves net zero energy operation without relying on batteries as much as possible. Please refer to the paper for details. Here is date collection block implementation. The battery on the back of the board is a coin battery for timekeeping. Next, I'd like to talk about lifelog generation block. Lifelog generation block is implemented in a smartphone application. It generates a life log using a machine learning model from recorded data extracted by a USB. Machine learning models are pre-trained and uploaded in the cloud. In the future extraction part, the data is segmented in a fixed length window, and 17 features such as mean, standard deviation, and peak-to-peak are extracted within the windows. As for machine learning model, we tried some typical classifier such as support vector machine and random forest and white GBM. The resulting output is subjected to majority voting within a fixed time. Next, I'm going to talk about evaluation. In this presentation, I'll focus on two evaluations. Evaluation 1 is accuracy of classifier. Evaluation 2 is battery usage. First, I'll explain about the experimental environment for evaluation 1. We conducted data collection experiments with 11 participants. The participants wore the device and lived through scenarios that cover multiple places and activities. Following previous studies, we limited the recognition targets to 8 places and 2 activities. Here are the results. Tenfold cross-validation achieved accuracy comparable to previous studies. But the accuracy of the place recognition was reduced in Leave One User Out cross-validation. Especially, the accuracy in restroom reduced significantly. We found out that this is because the harvesting energy varies greatly depending on the user's position in a place with few light sources, such as a restroom. The next is evaluation 2, battery usage. In the evaluation 2, we investigated the battery usage. We connected the data logger to the device and monitored the battery usage. The data was collected for 4 days from 10 a.m. to 7 p.m. and compared with the circuit that does not have battery usage minimization mechanism. Here are the results. By minimization, battery usage averaged less than 1% over 4 days, and battery consumption was only 10.32 nanowatt-hour. Considering from the capacity of the coin battery, it indicates that the ZEL enables lifelogging without battery maintenance on yearly basis. As a conclusion, I'd like to summarize the major points. We proposed the ZEL net zero energy lifelogging system using energy harvesters as sensors and power sources. ZEL can estimate place and activity with high accuracy and can continue to operate without battery maintenance in years by net zero energy operation. Wireless data transmission and device miniaturization are main future works. Thank you.